And so to tie this together with the things that we looked at in chapter 2, we can construct these discrete probability distributions from histograms and frequency distributions. So we're going to let x be a discrete random variable with possible outcomes x1, x2, all the way up through x sub n. So there's n many of them. We're going to first make a frequency distribution for all the possible outcomes. Then we're going to find the sum of the frequencies. Once we know the sum of the frequencies, so how many things are in our data set, we find the probability of each possible outcome by dividing its frequency by the sum of the frequencies. That's just a really long way of saying find the relative frequency of each possible outcome. And then lastly, we just need to make sure that each probability is between 0 and 1. Since we're taking relative frequencies, they should be between 0 and 1. And since we're going to be taking the sum of all possible outcomes with their relative frequencies, it should give us 1. So there are just a couple things that we have to check. Now let's look at this example here. So we're going to make a probability distribution from the following frequency distribution representing the number of fish caught in a 6-hour period. Let's say that somebody had the data set with a bunch of zeros, a bunch of ones, a bunch of 2s, 3s, and 4s. You sat there and you calculated the frequencies of each of those. So number of fish caught were 0. There was 88 total cases of those. 1 fish caught, there were 72 people that caught a fish. 2 fish caught was 30, and so on. Okay. And so if we first find, that takes care of this first step. We already made a frequency distribution. Next, we want to find the sum. So if we take the sum of f, we add up 88 plus 72 plus 30 plus 8 plus 2, which gives us a grand total of 200. And for each one of these, we find the relative frequency. So for this first box right here, we're going to take 88 over 200, throw that into our calculator to give us 0.44. And then for 1, we take 72 over 200, which will give us 0.36. For number 2, we take 30 over 200, which gives us 0.15. For 3, we have 8 over 200, which gives us 0.04. And then lastly, 2 over 200, which gives us 0.01. And so we double check. We need to make sure that each one of them is between 0 and 1 inclusive, right? Each one of these values is between 0 and 1. And then if we were to add these 5 numbers up, 0.44, 0.36, 0.15, 0.04, and 0.01, we will get 1. So this is our discrete probability distribution for this frequency distribution over here. And just like we had with frequency distributions where we can find mean, variance, and standard deviation to kind of give us a sense of where the center of the data is, as well as how spread out our data is, we can do the same thing with these probability distributions. So first, the mean of a discrete random variable, we have to account for the probabilities affecting how much certain things weigh. So if something has a higher probability, then the mean should be closer to that value than something that has a smaller probability, right? So again, we're going to take the sum of all x values, but then we're going to also keep track of the probability of that random variable. This should look kind of familiar. This is essentially the same thing as a weighted mean that we saw in chapter 2. And you may see it in your textbook, or you may hear me say it or something. But the mean of a random variable represents what you would expect to happen over thousands and thousands of trials. Since it's what you would expect to have happen, it is sometimes called the expected value. All right, so if that ever pops up on an exam or on a worksheet, expected value is essentially just finding the mean. And we'll denote that by E of X. Then once we know where kind of the center of the data is, or essentially what we would expect to have happen after so many trials, we can start talking about the variance, which is going to be very similar to our general variance formula. It's the sum of the squared deviations, and then we keep track of the particular probability. And then lastly, once you have the variance, you can find the standard deviation. Which is, again, the square root of the variance. Or if we want all the symbols there, it's the sum of the squared differences times the probability of that random variable, square root of that. Cool. So our last example is to calculate the expected value. And when you see expected value, we're really just talking about the mean. We also want to find the variance and standard deviation of the following probability distributions. So we have two of those. We have this first one, which was our first example of a probability distribution. Then we have this other one where we constructed it from the frequency distribution. So over on this side, we want to first calculate the mean. So if we unwrap the definition up here, it's the sum. So we're going to be adding together the random variable times its probability. So you take -5 times 0.5 plus 6 times 0.25 plus 9 times 0.25. Throw that into a calculator, you end up getting that the mean is 1.25. Right, so our expected value, if we had this frequency distribution, will be 1.25. And notice that even though 9 is the largest value that we have, it doesn't have a huge probability. 0.5 has a larger, -5 has about 50% of the weight over here, and there's only about a quarter of the weight for 6 and a quarter of the weight for 9. And so this 1.25 is kind of right around here maybe. It's not all the way in the negatives, but it's also definitely not pulled all the way up towards number 9. That leads us to calculating our variance. All right, so sigma squared, we're going to first take each value, so -5, and subtract off the mean that we just found, square that, and then multiply by the probability. So for this one, I'll write everything out. And for the next example, we're just going to throw it all into a calculator after we have it written down. So then we have 6 minus 1.25 squared times 0.25 plus 9 minus 1.25 squared times 0.25. Right, and the important thing here, I'm just going to do equals, I'm going to put PEMDAS. Right, remember the order of operations. You first take care of things inside the parentheses, then exponents, then multiply, and then you add. Right, so we're going to first do the subtraction here, then we're going to square it, then multiply, and we'll do the subtraction, square, multiply, subtraction, square, multiply, and then those three numbers we add together, and that'll give us our variance, which turns out to be 40.1875. And so the standard deviation, sigma, is the square root of the variance, which this will give us roughly 6.3394. Right, and so one standard deviation is fairly large compared to our actual values that we're looking at. And that's just because of the amount of spread in the data that we have. For this example, we have to first find the expected value, or the mean. whichever one you want to think of it as. So that'll be 0 times 0.44 plus 1 times 0.36 plus 2 times 0.15 plus 3 times 0.04 plus 4 times 0.01. Right, and we throw that all into a calculator, we get 0.82. Right, one way you can think of these means, if you had a bar that was, say, 4 inches long, and you put a weight of 0.44 at the very, very left end, and a weight of 0.01 at the far right end, and at the 1 inch mark you put a weight of 0.36, at the 2 inch mark you put a weight of 0.15, and at the 3 inch mark you put a weight of 0.04. Then what this 0.82 represents is to perfectly balance the weights on this 4 inch bar, you need to put essentially a fulcrum, or the point at 0.82 to perfectly balance this thing with the weights. Next, we want to calculate the variance. So again, we'll do 0 minus 0.82 squared times 0.44 plus 1 minus 0.82 squared times 0.36 plus 2 minus 0.82 squared times 0.15 plus 3 minus 0.82 squared times 0.04 plus 4 minus 0.82 squared times 0.01. All right. If you have a graphing calculator, you can plug this whole thing in one shot. Just be careful with your parentheses and where you're putting your squareds. So I would suggest maybe pausing the video if you have a graphing calculator and trying to calculate this out on your own. Come back once you have that, and what you should be getting is 0.8076 for your variance. If you got 0.8076 after plugging into your calculator, you're good with calculator skills, and so you can just plug it all in one shot. If you ended up not getting this value, be careful with your parentheses, your exponents, multiplication, and addition symbols. You can do it step by step, where you can take the difference, square it, then multiply it, and just keep track of what this is, and then do that for each one of those, and then add them up afterwards if you'd like. So you can do it step by step, or you can do it all in one shot. And then finally, the standard deviation, which again is the square root of the variance, should give you 0.8987.